So the next topic that I would like to discuss is really droplet combustion, which is of course related to spray modeling. And just a few words about spray. Of course, it's a very important subject because many practical application of liquid fuel are, when they are injected into a combustion chamber, they result in a fuel spray. Well, you need to atomize the liquid fuel. The liquid fuel cannot burn as a sheet or as a volume of liquid. And so you want to atomize it. You want to break it into small droplets, because then the droplets would have a larger exposure to the oxygen and can burn more efficiently. And typically, you're talking about a very, very large number of droplets. So, for example, if you atomize 1 centimeter diameter of droplet 1 centimeter diameter droplet of liquid into droplets of 100 micrometer, just because of because they must have the same volume, then the 1 centimeter diameter droplet will produce 1 million droplets. And that will increase the overall surface area by a factor of 10 to the 4. So clearly, you want to break them into very small droplets. Now, the spray combustion in general is very complicated because it involves many physical processes. The first thing is the atomization that I just mentioned. Then a droplet may collide or agglomerate. They will vaporize. There is heat and mass transfer involved. And then mixing between the droplet, the vapor, and the air. And there will be ignition, typically under turbulent condition. And you may have either premixed or diffusion flames involved in such a burning situation, etc., and flame extinction and so on. And here's a picture of just to show some of these processes. You have here the liquid jet that breaks into many droplets, and you have the oxidizer, which is entrained from the environment, from outside. And then, first of all, you can have an enclosed diffusion flame where they burn, but you can also have single droplet that burn individually, or you can have a group of droplets that burn together. They can burn in the middle, or they can burn more at the surface. And all these can happen under different conditions, different circumstances. So clearly, it's a very complicated process. There is, in the end of this lecture, there are a few discussion of different modeling attempt, numerical modeling attempt of spray, and you will see that there are few, I don't know if I will get to discuss this in detail, but certainly not in detail, but to give you an idea of this, but if not, you will read it there, and you will see that it's rather complicated to do. So for example, if you were to do a direct numerical simulation, in other words, without making any assumption, if you want to solve the problem, what you have to do is to identify at a given time of your simulation all the blue droplet and all the rest, which is, say, the gas outside. Then you have to solve one set of equation inside every droplet and a different set, which are the liquid phase equation, and then a different set of equation in the gas phase. And then you have to track the size of those droplets, because as they vaporize, they, of course, shrink, right? They reduce in size. And so you have at every instant in time to track all the droplets in your field and to identify what they're going to be at the next stage, whether they will still exist or not, whether they will agglomerate with other droplets, whether they will collide and break into 2 droplets, and so on and so forth. And so clearly it's an impossible task, okay? And so there are, of course, other simpler methods that people have done. Or if you track the droplet, for example, you track them as particles, and you follow the dynamic of these particles. By the way, when I first said the complication, I stopped short of saying, well, you have also to account for the boundary condition, what happened at the surface between the liquid droplet and the outside gas. And so it's really a very, very complicated problem. And certainly it gets even more complicated because of the number of droplets, which are, as I indicated earlier, that it's a huge number of droplets that you have. Typically, they range between few micron to 500 micrometer, and you can find, where did I say that? You can find that the number of droplets is humongous, and so it's really a very, very complicated problem to do it from first principle. And so there are some way to simplify the system. At any rate, one of the most fundamental problems in this setup is to discuss how does a single droplet burn, okay, vaporize and burn. And so the focus at the moment will be on a single droplet. So droplet vaporization and combustion. So you have a droplet of liquid fuel that vaporizes and burn, or does not burn, then it's pure vaporization. So we'll do both cases, and burn at a spherical flame that is surrounding the droplet. So first of all, as we are going to make a few assumptions, the droplet is a sphere, which is a reasonable assumption actually, and it burns in a spherical symmetric fashion, that it consists only of a single fuel. You see, if it's a mixture of more than one fuel, there's complication because one vaporizes before the other, and so at the surface you may have the vapor of one fuel and not the other. It's already more involved. So we're going to assume a single component fuel. We're going to assume that the properties inside the droplet are uniform. So in other words, there is no diffusion of the liquid fuel, and the temperature is uniform. We're going to assume that there is no fluid motion inside the droplet. Of course, that's not entirely true. Sometimes you may set up some internal motion inside the droplet, but we're going to assume that that's absent. We're going to assume that the droplet is vaporizing in a quiescent atmosphere, and later I will tell you something about what happens if it's in a let's say in a combustor, where there is a relative velocity with the fluid inside say the combustor, so we're at the moment the ambient is quiescent. So in other words, the velocity is equal to 0, and the droplet is vaporizing in this quiescent ambient. We're going to neglect gravity, and we are going to make this assumption. I'm going to discuss it in more detail, the quasi-steady approximation. The chemistry will be described by a one-step chemistry, fuel plus oxidizer, go to product. And so this is the setup, and the first thing that I would like to discuss is the sum of the quasi-steady approximation. So if we focus on the mass of the liquid inside the droplet, which is the density of the liquid, right, multiplied by the mass, multiplied by the volume, which is 4/3 pi Rs cubed, right? And we ask, what is the time rate of change of the mass of the liquid? Well, it's going to be equal. Of course, it's going to be reduced in time. In other words, the droplet shrinks, and so the mass, there is a mass loss, if you like. That's why the negative sign. And that's equal to the mass that is essentially leaving the surface of the droplet, right? And that statement is, in fact, written in the next line. The derivative of the volume, the only thing that changed here, assuming that the density of the liquid is constant, is the radius. And so the derivative of Rs cubed is going to be 3 times Rs squared, right? So the 3 and 3 cancel, so you get only 4 Rs squared dRs dt. So that's the derivative on the left. And on the right, that should be equal to the mass that it's leaving the droplet, which is the vapor. So it's equal to the area multiplied by the density of the gas. and the relative velocity, the velocity that the gas is leaving the surface relative to the receding droplet, right? So that's the relative velocity, which when you cancel the 4 pi r square on both sides, you get simply this relation. Well, but that's exactly a direct consequence, even though I described it in words, it's a direct consequence of one of the jump relations that we have derived in one of the first lectures. Remember, I told you that we can derive jump relation across an interface. An interface could be liquid gas or something else, if you like, solid gas, gas, whatever. And we derived this using this pillbox argument. And one of the relation was the following, that the flux in is the flux out, but relative to the moving surface, right? So if you apply this to the droplet, you're going to see the following. Inside the droplet, there is no motion, so V is 0. So the left-hand side is rho, which is rho liquid, times the velocity of the interface, which is dRs dt, right? And on the gas side, you have rho gas, the velocity of the gas, which is V, because it's only the radial component that we have in a spherically symmetric situation, minus the velocity of the interface, which is dRs dt. So this relation is either from here or from just argument of global mass conservation of the droplet, clearly, right? Now, this relation, now there is one notice that the relation involved the density of the liquid and the density of the gas. Typically, the density of the gas is much smaller than the density of the liquid. Typically, it's like 10 to the minus 2, 10 to the minus 3. And so if we assume that this ratio is small, then it implies that dRs dt is equal to minus rho gas over rho liquid V, because this dRs times rho gas is much smaller than this dRs times rho liquid, right? And so this is the approximation that you get. So in fact, that's a good relation, that once we obtain the velocity of the gas just on the vapor side, then we can come back to this relation to determine the history of the radius, or how does the radius change in time, which we will do. So I framed this because we're going to get back to it. However, that relation indicates one more thing. It tells you that the radius recedes, or the droplet recedes very slowly. Why? Because it's proportional to the density ratio, rho gas divided by rho liquid. And so it recedes very slowly. If it recedes very slowly, the gas phase are almost in steady condition. Namely, as the droplet recedes from one radius to another, there is no very much changes in the gas, and so we can compute the gas phase from the steady equations. And so this is the essence of the quasi-steady approximation. So we can compute the velocity V or the mass flux rho V in the gas phase from steady equation instead of unsteady equation. In other words, in principle, the problem is intrinsically unsteady. Things vary in time, things vary in time, and so the liquid phase and the gas phase both will change in time. However, because the density ratio is small, the gas phase variation are relatively slow and can be treated as steady. So we're going to solve, in fact, steady equation, spherically symmetric, so this is the kind of equation that we're going to solve. Mass conservation in spherical coordinates, right? The equation for YF and YO, the energy equation, here is the heat release, lambda is the conductivity, and so on. So everything here is known to you. The equation of state with P dot constant, and the reaction rate for these two component fuel and oxidizer. Now, there will be boundary conditions which are obvious. For example, the boundary condition at infinity is clear. The temperature is known, the density is known, there is no fuel at infinity, there is only oxidizer. But what about the boundary condition at the surface of the droplet? Well, this is a bit more complicated, and we have to spend a few minutes to describe that. So this is what the discussion is now. Again, I'm going to use this interfacial jump relation that we derived earlier on Monday. So one of them is about the different mass fraction, which is written here, right? If you go back in your note, you'll see that one of those jumps is this. Of course, we had a term here that was related to the reaction term, but we are assuming that on the surface of the droplet there is no reaction, and so it's equal to 0, okay? And this VI is the diffusion velocity, and this VI is the interfacial velocity, the velocity of the interface, the RS dt. So if we write this expression, on the left is the gas phase, on the right is the liquid phase. So the gas phase, you will have rho, yi, the velocity is v minus drs dt, which is this, it's rs dot, okay? And then the diffusion velocity is, by Fick's law, is equal to, or it's proportional to the gradient of yi, right? So rho gas yi vi is the same as rho I di diffusivity times the gradient. That's Fick's law for this term here. So this is on the gas phase. On the liquid phase, we have assumed that there is no velocity, there is no diffusion, right? We assume that in the droplet we are neglecting any motion. There is no diffusion. And so the only thing that survives in the liquid phase is the fact that is rho L multiplied, right? The liquid density, yi, multiplied by this vi, which is drs dt, rs dot. Okay? So this is exactly that relation with the assumption that we have made in the liquid phase. Now if we take in addition the assumption that rho gas over rho liquid is small, and which implies that rho gas rs dot is small and rho liquid rs dot is approximately rho gas v, which is the relation in the previous slide, then this relation simply reduced to this for the fuel, okay? In other words, you see this is this term, this is the diffusion term, this is negligible, right? Right, it's negligible. And on the liquid side, rho L rs dot is replaced with rho gas V. In the oxidizer side, you are going to obtain a similar relation, except that there is a 0 term here because there is no oxidizer that is diffusing in the droplet. Okay? Inside the droplet, Y oxidizer is 0. Right? There is only fuel. So these are, in fact, the two boundary conditions that you obtain, and they can be interpreted very simply. This is the convective and diffusive flux. So this is the net flux. So this is the net flux from the gas phase towards the droplet, and that should be balanced by just the flux outside that leaves the droplet. And the net flux of oxidizer must be 0 because there is no flux of oxidizer from the droplet. Okay? So it's a simple interpretation. The next equation or next boundary condition we wanted to consider is the energy equation. Again, if you look back in your note, you're going to see that this is the interfacial condition that we derived for the energy interfacial condition. And we can now express it again as before. So in the gas phase, so we have the density of the gas, the enthalpy of the gas, rho gas, H gas, and then V minus Rs dot, right? And the heat, that term goes away. I'll explain to you in a minute. The heat flux is essentially only the conduction, heat conduction, and so it's the lambda gas. By Fourier law, it's just the derivative, the gradient of the temperature. And A plus indicates it's on the vapor side. A is, should be RS instead of A, but I'm going to use A instead of RS in the next slide. In the liquid, then there is the density of the liquid, the enthalpy of the liquid times RS dot. There is no velocity, so this is 0. And the heat flux is just by Fourier law. Again, it's the conductivity of the liquid dt dr. Now, there is no reaction, and so the term with reaction is gone. And we have, of course, neglected from the original equation the kinetic energy and the viscous dissipation, which is basically in line with the small Mach number approximation. And then if you, in addition, use the fact that the density ratio is small, then this relation simply reduces to what's in this line here, which is the difference in enthalpy between the enthalpy of the gas and the liquid, which is nothing more than the latent heat of vaporization, okay? Minus just the net flux of energy due to conduction, okay? Now I'm going to interpret this a bit next in a somewhat simpler way, which is written here. So, well, actually it's the same. So what this state is this relation state in physical terms is the following. The temperature gradient or the heat flux from the gas phase towards the droplet, right, go partially to heat up the droplet, which is the gradient inside of the temperature, the heat flux inside the droplet. It goes to heat up the droplet. And part of it go to vaporize the droplet, which is the latent heat of vaporization. Now, since we have assumed that properties inside the droplet are constant, then really this gradient that go inside the droplet can be estimated as what have caused the change in the temperature of the droplet over time. And it's easy to interpret it as the entire heat flux go into heating the content of the droplet in this volume 4 pi a cube. And so, again, here is the interpretation I said before. The heat conducted towards the droplet is used to vaporize the droplet, where QV is the latent heat of vaporization, and part of it go to heat up the interior of the droplet. That part is usually neglected, or some people, instead of the latent heat, take an effective latent heat, which is the latent heat minus something that is used to heat up the droplet. So it can be accounted for by assigning the value of QV. We're going to neglect it simply, but you can interpret QV differently if you want. So the boundary condition at the interface is going to be just that, namely that the heat conducted back to the droplet is used to vaporize the droplet. Okay? So this is the other boundary condition. Now these conditions are not sufficient because you see, in addition to, so we have derived 3 conditions in addition to these boundary conditions at infinity. One for the fuel, one for the oxidized, one for the temperature. But this equation also requires determining the mass flux, which is rho v leaving the surface, which is going to be associated with the vaporization rate or the burning rate. Okay? And so we need one more condition. And the additional condition that need to be used come from equilibrium condition at the interface, at the vapor-liquid interface, which is essentially the Clausius-Clapeyron relation that state that the partial pressure, okay, near the interface is a function of the temperature, or is related to the temperature. But this expression is a bit too complicated for simple analysis, and so instead we're going to use essentially a simpler version of it, or a simpler boundary condition, that the temperature at the surface is known, and I will say TB, let's say the boiling temperature. So in order for the droplet to vaporize, we will assume that the temperature at the surface, and therefore of the droplet, because we are not assuming any variation inside the droplet, is the boiling temperature. So we end up with these 4 boundary conditions. The flux of fuel is known, flux of oxidizer is 0, the heat conducted back to the droplet is proportional to the latent heat of vaporization, and the temperature at the surface of the droplet is known. If we non-dimensionalize this equation, and we use now, I'm going to just drop the subscript G from the rho G, so I'm using density rho for the gas density. And for the time being, I'm going to call the radius A, but I'm going to revert back to RS later on. And so these are the equations, and if I make them non-dimensional, then these are the equations and these are the boundary conditions. Just to make sure, how do we non-dimensionalize things? We use the condition at infinity to non-dimensionalize temperature and density. And the mass fraction are already dimensionless, so they don't need to be normalized unless you want to. And M, which is related to the mass flow rate, is going to be normalized with this quantity. So capital M is the dimensionless mass flow rate. Okay? Since R square rho V is a constant as a result of continuity, then everywhere rho V in these equations, in other words, the convection term, rho V is replaced by M over R squared. So these are essentially the equation that you are solving. And the Dam-Kohler number here is, again, as before, the ratio of the flow time to the chemical reaction time. But as is defined, where did I, oh, it's here. Here are the parameters. They are defined here. So we are going to also have the heat release Q, the little q, which is the heat release divided by the enthalpy of the ambient temperature, at the ambient temperature. The LV is going to be now the dimensionless latent heat of vaporization. And the Dam-Kohler number that I want to emphasize is proportional to A squared, which is the droplet radius. So increasing D is increasing the droplet, but I'm more interested in decreasing D. Decreasing D will make a smaller droplet. And also D is proportional to P naught, the pressure. Okay? Remember that because we're going to get back to it. So for simplicity, I'm going to assume unity Lewis number, but we know how to construct now the solution even for non-unity Lewis number. I mean, since it's a diffusion flame, we already seen how to do it in both cases. The relations are a bit more complicated, but it's simpler to deal with the unity Lewis number. So these are, again, the equation that we want to solve, and these are the boundary conditions. And if you count number of equations, you have 3 second-order equations. So you have a 6-order system, and you have 1, 2, 3, 4, 5, 6, 7 condition, which is 1 more because you need to determine the mass flow rate, capital M, which is either the vaporization rate if it's pure vaporization, or the burning rate if it's also combustion. Okay? Now, the operator that all these equations involved is something like that, and that operator has solution of this form, e to the minus m over r plus a constant. So we can very quickly write the solution. So we start with pure vaporization, d equal to 0, Dam-Kohler number, no reaction. And the solution is simply YF and YO and T as expressed here, and M is given by this relation. So let's put M in dimensional form. Dimensional form, we obtain that the mass flow rate, M dot, is equal to this expression 4 pi A, lambda over Cp essentially, it's from the conductivity divided by Cp. And the log of this expression, 1 plus this factor, or this ratio of 2 things. Well, this ratio of this quantity, which is the ratio of two quantities, is often referred to as a transfer number. In the numerator, what you see is CPT infinity. It's a difference between the temperature at infinity, the ambient temperature, and the temperature of the droplet surface. And so what it is, it's an impetus for transfer, right, for heat transfer. In other words, the larger it is, the more vaporization you have, the more vapor leave the droplet. What you have in the denominator is the latent heat of vaporization, which resists the transfer. So in fact, this ratio, it's often called the transfer number, and it's just the ratio of these two effects. So, and clearly, this transfer number, sometimes is known as the Spalding transfer number, is positive when T infinity is bigger than TB, which means that you need heat to be transferred from the ambient to the droplet so that the droplet vaporizes. Otherwise, it will not vaporize, right? So the only possible solution is when T infinity is bigger than TB. And so this is the pure vaporization, and I have denoted the transfer number by B subscript V, for V stands for vaporization. The next case is, so here is just a graph of the solution. You have the mass fraction that drops, goes all the way to 0 of the fuel, and the temperature of the droplet is TB, and then it increases all the way to T infinity. So heat is conducted this way, it vaporizes the droplet, and the vapor is diffusing out. There is no oxidizer, it's because there is no reaction. It's not important. So the next case is going to be combustion. With combustion, then since we have assumed unity Lewis number for simplicity, we're going to use the coupling function. So if we use the coupling function, we have that T plus QIF, we can write the solution for it, and we can also write the solution for T plus the combination T and YO. And we can also take the difference and write the combination YF and YO. Okay, so the first thing is, if YO is 0, you get the profile of YF in the region where there is no when there is no oxidizer. And then if YF is 0, you get YO in the region where there is no fuel. So immediately you have the solution for this. In addition, if both are 0, you get the location of the sheet, which is the radius RF, where the reaction occurs, which is not written here, but will be written next. And then from these two relations, these two coupling functions, immediately get the temperature, because where YF is 0, you get the temperature. Where YO is 0, you get the temperature. The temperature is given then by those two expressions, right? Okay, since we have one more relation, right, which is we know the surface temperature of the droplet, then we apply that condition, we get the burning rate M. And if we put it in dimensional form, this is what the form it takes, okay? And so what you see, it's that, again, it's logarithmic of something which is the impetus to transfer divided by the resistance to transfer, but now the impetus to transfer involves also the heat release, right? And so the transfer number, the combustion transfer number B with subscript C is slightly different than before in that it includes also the heat release. Okay, so we obtain now the burning rate with combustion and for pure vaporization. Of course, combustion M dot is larger because this is positive, it's a larger value. And we also can write expression for the position of the flame of the reaction sheet, RF, and for the flame temperature, which is the temperature where the fuel and oxidizer both vanish, okay? And here is a graph of the solution. And so you have the temperature increase to the flame temperature. This is the location of the reaction sheet, and then decrease to T infinity, where T infinity is bigger than TB. And then the concentration, the mass fraction of the fuel decrease to 0, stay at 0. The mass fraction of the fuel decrease to 0 and stay at 0. And if, so this is the Burke-Schumann solution, which correspond to situation where the temperature is the flame temperature is the highest, and the fuel and oxidizer are totally consumed at the sheet. Okay. Now, what happens if you decrease the dam color number? Here are a few numerical solutions for smaller values of D, because for smaller value of D, you have to solve the governing equation with the finite rate chemistry. You cannot assume D going to infinity. And so what you see is that the flame temperature slightly drop, and here are curves of the mass fraction of the fuel and oxidizer, and you see that the reaction zone become a bit thicker and thicker, right? It's not just the sheet where everything is consumed, but it's somewhat thicker. Now, it's not very large as maybe you see here. It's just that I didn't put here any scale. So on the normal scale, it's really quite thin. Okay. And the present problem also include, or the response of the system can be also described by an S-curve, as we have seen before in other diffusion flame problem. So when D goes to 0, you get a pure vaporization. So this is this green limit, which is the vaporization limit. And if I plot here the burning rate as a function of the dam color number, this is going to be the MV, the vaporization limit. Okay, the burning rate for pure vaporization. And of course, it's smaller than the combustion, the burning rate for complete combustion, which was obtained by the Burke-Schumann limit, and it's a value here that, remember the difference was that the transfer number here is B combustion, which is larger than the one for pure vaporization. So the two limits, we have derived these two limits. And of course, the response for intermediate value of D will follow this S-curve, as before, with an ignition and an extinction condition, or ignition and extinction limit. In particular, remember that the dam color number was proportional to the droplet radius square, which means that a large droplet will burn at, let's say, they will have a strong burning. They will burn completely, but as they become smaller and smaller, there will be a critical radius below which the flame would extinguish, and it will happen at small radii. So you have like an extinction condition for small droplet. On the other hand, you can think of a pure vaporization where you increase D, so eventually you would have a larger droplet that will auto-ignite. So you have an auto-ignition, auto-extinction, if you want. You can also interpret this result by varying the pressure, right? You increase the pressure up to a point where ignition occurs, or you decrease the pressure of a strongly burning droplet to a point where extinction would occur. So it can be caused by one or the other. Okay, so now that we have computed the burning rate, we go back to one of the first equations that we have derived, and we want to describe the droplet history. So remember that the relation was that the relation was that the Rs dt, right, the history of the radius, or the time rate of change of the radius of the droplet, is equal to minus the ratio of the gas to liquid density times V, which was the velocity of the vapor leaving the surface. Now V is related to M, or M dot, right? And so if we substitute M dot for V, and we also express or use the fact that rho V is what we have. Well, rho V is what we need in this expression, but we use the expression for M dot, which was obtained before in the form of 4 pi Rs times lambda over Cp, the log of 1 plus b, with b being either the vaporization or the combustion transfer number, right? So if we substitute for m dot here, and we obtain rho v, and we substitute in this equation, we see that the time rate of change of Rs is inversely proportional to Rs, with k being a constant, which is written here. And so this equation now can be, or if you bring in the Rs on top, you can immediately see that this is the derivative of Rs squared. And so the derivative of Rs squared is a constant, tells you that Rs squared drop or decrease linearly in time. And usually this expression in the literature is written in terms of diameter instead of radius, and it's known as the d square law. Accordingly, the diameter square decrease linearly in time, and capital K is the evaporation constant and is given by this expression. And it depends if it's pure vaporization or vaporization and combustion that what the value of B is. In particular, if this drop linearly, when we can compute immediately is the lifetime of the droplet, which is the time when the diameter goes to 0, which is 1 over K. And so here is an expression for the lifetime of the droplet, okay? And remember that the density ratio rho liquid divided by rho gas is rather large, and so the lifetime is relatively large, relatively, of course, relative to the gas phase processes. Okay, so this is the d square law, and you see that experiments show that the d square law is quite valid for probably most of the lifetime of a droplet, with the exception of a small time interval which is close to the ignition, okay? But after this small time interval, then follow the straight line as predicted by the d square law, okay? Now, yeah.
Why didn't we see the extinction in the experimental data? I mean, when the radius is pretty small, there is no extinction in the experiments?
Well, the extinction may not always happen because, you know, the Dam-Kohler number is not only affected by the droplet size. And so it could be that when the droplet was very small, even the radius approach 0, you are still on this part of the curve where the Dam-Kohler number is still sufficiently large, right? So you don't, I mean, I do not argue or claim that there is always a critical radius where extinction will happen. But one thing that could affect the change in Dam-Kohler could be the radius, okay? So you see, in other words, there are more than one effect. Sure. So we discussed so far the behavior of a single droplet in a quiescent atmosphere. Now, what if the droplet is in a combustion chamber? Well, then the behavior of the droplet will depend really on the Reynolds number, which is defined with respect to the velocity of the particle, namely the droplet, relative to the velocity of the gas in the combustor. And so, in other words, what we have discussed is a situation where the Reynolds number is 0. But typically, the Reynolds number is going to be not 0 and large. And so the question is, how does the result that we have shown are affected by the relative velocity? Well, this is usually, in the literature, addressed by some empirical correlation, where the evaporation constant is expressed as the evaporation constant for quiescent condition. It's what we have derived just a few minutes ago, with a correction term that is proportional to the Reynolds number to the 1/2, Prandtl number to the 1/3. And typically the constant in front is of something like 0.3. Remember that this is an empirical correlation obtained only from experimental data. Okay. Similarly, one can also ask what is the burning rate or the correction of the burning rate as a result of free convection. And again, one can write the evaporation constant as the evaporation constant for quiescent condition, as we have derived before, with a correction term that is proportional to the Grashof number raised to some power. And here it's about 0.52. The Grashof number now is defined here, right? And note that it's proportional to the gravity, and it's also proportional to the density of the gas square. And so under what condition does natural convection or buoyancy is not important? Well, in other words, when can we expect that K is approximately the evaporation constant in pure for quiescent condition? Well, it can be obtained in two cases, either under zero gravity condition, right, and the Grashof number is 0, or under reduced pressure, because then under reduced pressure, the density would be small. And so then the Grashof number is small, the correction is small. So you can obtain an almost spherically symmetric flame also in reduced pressure environment. And people have done that experimentally. One can extend the discussion of a fuel droplet to particle, solid particles. So for example, think of a solid particle being a carbon particle or some metal that is burning. And one can, in this case, in fact, obtain more than one behavior of the burning. One of them is similar to the droplet case, which is the diffusion control limit. In other words, you still have a diffusion flame that stands away from the particle, but since it doesn't really stand very far from the particle, then in the transfer number, you can assume that the oxidizer mass fraction is the oxidizer mass fraction in the vicinity of the particle, okay? And so in this case, the mass burning rate, m dot, similar to the expression that we have derived before, is going to take this form, where the only difference from before is that instead of lambda over Cp here, I replaced it with rho gas times the diffusivity of the oxidizer, okay? And this is, if you assume that the Lewis number is 1, then clearly those two factors are equal, and so that's exactly the expression that we had before. And so this is under the diffusion control limit. But, that limit leads to also a d-square law, similar to what we have seen before, where the lifetime of the particle is going to be now the density of the solid divided by the density of the gas, and multiplied by a factor which is very similar to what we had. So essentially, we had a d-square law under diffusion control limit. In other words, that the burning is essentially controlled by diffusion of oxygen towards the particle, as similar to the droplet case. But there may be a situation in which the burning occurs at the surface of the particle or inside the pores that we approximate by being at the surface of the particle. And this is controlled by the chemical reaction that occurs at the surface. In other words, m dot is going to be proportional to the rate Ks that the reaction occurs at the surface. And that is temperature dependent, of course. And so in this case, the mass burning rate m dot, which is equal to the change in the or the mass loss of the particle, right, like we have done before, is going to be equal to this expression. In other words, it's going to be driven by or dictated by the kinetics. And as a result, one obtains an expression for d, which is not a d square, but d to the power 1. So kinetically controlled is lead to a d to the power 1 law, a linear law, rather than d square. And the lifetime is, as described here, again, it's obtained by setting the diameter d equal to 0 and obtaining for a given initial diameter d naught what is the time that the particle has been totally consumed. So one can, in fact, see that the lifetime of the particle depend if it's diffusion control or kinetic control mechanism. In one case, you obtain this relation, in the other case, this relation. The diffusion control limit show that the time, right, the lifetime is independent of the temperature, and it's proportional to the square of the initial diameter. The kinetic control limit show that the time depends on temperature, right, through the Arrhenius dependence, and that it's proportional to the diameter to the power 1. And one can therefore describe or define a surface dam Kohler number, if you like, which is going to be the ratio of these two times, diffusion control, kinetic control, and it's given in this expression. And as a consequence, you can identify that, let's say, if you have a combustor where solid particles are burning, let's say coal, then that the large particle or the large particle are going to be burning under the fusion control condition, and the small particle on the kinetic control condition. It can be also interpreted in terms of the ambient temperature. But you see, this complicates business because what you have is large particle, as time proceeds, shrink and become small, so they change from one behavior of diffusion control to a different behavior of kinetic control, and so it complicates, of course, the simulation or the analysis if you want to prescribe a certain behavior to the combustion of the particle. I think I will more or less stop here. I did say few words about this in the beginning, and I told you the complication that arise if you want to really do a direct numerical simulation of a spray problem because of the large number of droplets, because of tracking all the particle, how they shrink in time, and solving the equation inside and outside the particle, including the boundary condition and so on. In the literature, you'll find that there are few approaches to do that. There is a continuum formulation, there is a Lagrangian formulation, probabilistic formulation. I wrote few very brief description of this in the notes, so I will let you read them and just get an idea of them, but really to fully appreciate that, you will have to go into the literature and examine this in more detail. So thank you very much, and we will see you tomorrow.